Welcome to the video lecture by Dr. Biju Vasudevan for the course Calculus 3 Math 211. This video is for week 12, which we will discuss the chapter 13.8. We call it maxima and minima of functions of two variables. Maxima and minima of functions of two variables. Earlier in Calculus 1, you must remember that we have seen how to find maximum and minimum values of a function of one variable. In this section, we just extend the concept for function of two variables. Look at the graph shown on this page. If we consider the graph of a function of two variables shown in this figure as a mountain range, then the mountain tops shown here, and mountain tops, which are the high points, are in their immediate vicinity. In this locality, this is the highest point. In this locality, this is the highest point. In this locality, this is the highest point, isn't it? We call it relative maxima in this locality, isn't it? So similarly, in the bottom points, the bottommost points, isn't it? Valley bottoms are called these points. In this locality, they are the minimum values of this locality. So we call this one mathematically a relative minimum. This is called a relative maxima and minima. And if a geologist wants to find the highest mountain and the deepest valley in the highest mountain top and the deepest mountain valley in the entire mountain range, extend it for the entire range. We want one peak and one valley in this entire range. Then we call it mathematically is absolute maximum and absolute minimum. For example, in this entire graph, this is the highest peak, isn't it? Highest peak point, and this is the deepest valley. So this is the highest peak. We call it absolute maximum of all maximums, and this is absolute minimum with the entire range. If this happens in the entire domain of the function, we mathematically interpret it as the domain of the function, then it is absolute maxima or absolute minima here, right? Fine. Let's go to the proper definitions right now. Definition says that a function f of two variables is said to be relative maximum at a point x, x0, y0 if there is a disk centered at, so for example, if this is the let's stop for a while. If we find here such a curve, such a shape, and if this is the point called x0, y0 on the ground, isn't it? In this locality, for any pair of xy, you can find f of xy, but the value should be lesser than the value of f of x0, y0. Then if this value, function value at this point x0, y0 is greater than any other point in this locality, we call this as maximum. This function is getting relative maximum at this point. The same can be interpreted as for relative minimum. If you find such a curve on this point x0, y0, and in this entire locality, this is the minimum most value of the function, then you can say at this point the function has a relative minimum. Some graphs will be like this. You can say one side it going up, another side is going down. Your point may be here. When you draw a circle, small circle in the neighborhood, for some point the function, if this points x0, y0, it will be lesser than for any xy. Sometimes this value, the function value at this point will be lesser, or sometimes it will be greater. So in this case we will not find any relative maxima or minima. Alright, let's go to the next definition. The graph shows what is relative, mathematically what is absolute maximum, absolute minimum. This is the point at which absolute maximum, maximum of all maximum. This is relative maximum. In this locality, this is the maximum. In this locality, this is the minimum, relative minimum. So this figure gives an idea what is absolute maximum. Absolute maximum occurs at this point and absolute minimum occurs at this point. In between, you can find relative maximum and minimum. So this is about boundedness. See, the first graph is a set of points in two space. This is set of points in two space. This kind of space is called bounded if this entire set can be contained within some rectangle, such a rectangle, isn't it? If this is possible to contain this range, this space in one rectangle, we can call it a bounded space. But here, see, this is not bounded because the entire xy plane cannot be xy positive quadrant. First quadrant cannot be bounded, so there is no rectangle that bounds this one. So this is unbounded region. Here in 3 space. Similarly, the third graph gives us a set of points in 3 space, which is bounded if the entire set, this set, can be contained within some box. If there is no such a box exists, then we call it unbounded. Next, we go for extreme value theorem. If a function f of xy is continuous on a closed and bounded set R, closed and bounded, it should be closed and bounded. Bounded, the dimension we have seen right now, and f should be continuous in this region R. Then f has an absolute maximum and absolute minimum in this domain, in this R, in the region R. So if one of these condition fails, then there is no guarantee that there is an absolute maximum or absolute minimum. If it is not continuous in the closed and unbounded in the bounded region, so you will not accept. You cannot expect some absolute and absolute maximum and minimum. If it is continuous but the region is not closed or bounded, still the statement is not true. So next theorem. F has a relative extremum at a point x0, and if there is a first order partial derivative of a then its first derivative is 0. If the first derivative exists, first partial exists, then we can say the derivative is 0. It means that the relative extremum, relative maxima, minima are occurring at the points which are called critical points, CP, just like your function of one variable. So definition says that a point x0, y0 in the domain of a function is called critical point if the either the first partial derivation will not exist at the particular point. If exists, it is 0. That is the minimum. So just like our function of one variable, critical point, the definition of critical point is the point at which first derivative will not exist. If exists, it is 0. Right? Fine. Now some graphs. What is the case? This is the point at which see the slope is 0 in this direction. In this direction, so slope is 0. So if the first derivation exists at this point, it is 0. So this is at this point relative maximum, because if you extend, and this can be absolute maximum as well, if you extend it downwards, it goes towards the minimum value. There is no more maximum values, only one maximum value at this point. This is a relative maximum, and of course relative absolute maximum as well. So this is the point that we have already seen, a point at which no maximum or no relative maximum or no relative minimum, because If you draw a locality, I mean a small circular disk about the point 0, 0, on some for some points f of xy is greater than f of x0 y0. Here x0 y0 0, 0. For some points f of xy will be less than f of x0 y0. X0 y0 is 0, 0. So it is not true for all the points. One statement is not true for all the points in the circle. Therefore, there is no relative maximum nor relative minimum at this point. So some other graphs that will show you relative absolute and relative maximum. I can go through this one. And the second partial derivative test for finding relative minimum and relative maximum. And important thing, we know there is a function f of x comma y, isn't it? And you should remember that r, s, p, q, r, s, t are the fundamental notation for the first derivative. What do you mean by p? P is first derivation of f with respect to x. Q is first derivation of first partial derivation of f with respect to y. This is also partial derivation. So then what is r? R is f double x. T is f double y. And what is s? S is fxy or fyx. Second derivation of f with two different variables, fxy or fyx. We should remember these 5 letters that represent the first two represent the first derivative, last 3 represent the 3 different second derivative terms. If you remember this one, we can simplify this formula into a different case. We can write this d, discriminant d. D stands for discriminant, isn't it? It is rt minus s square, very simply. Rt minus s square. Hereafter we are going to use this formula, rt minus s square. R is second derivation with respect to x, t is second derivation with respect to y, and s is second derivation with respect to first with respect to x, and then y, or first y then x, whatever the order is. Okay, now let us start again this formula, the rule, what we gotta do to find the relative extrema. If you are given a function f of xy, first step is find fx and then fy. We call it p and q, isn't it? And then make them equal to 0. Fx equal to 0, fy equal to 0. Take them 0, because we know if the first derivative exists, it is 0 for critical point. And moreover, the relative extrema occur at the critical points. So we are supposed to find the critical points, isn't it? Let the fx equal to 0 and fy equal to 0. You may get some. When you solve these two equations, you will find the values of x and y. So we can pair them to get a certain number of points. We call them critical points. There will be x1, y1, there may be x2, y2. There may be many pairs. When you find, if you get x equal to plus or minus 2, y equal to plus or minus 1, there are 4 pairs. X equal to positive 2, y is equal to positive 1, x equal to positive 2, y equal to negative 1. So if you pair all the numbers, you get 4 different pairs. So we equate first derivatives into 0 and then find the values of x and y, take the pairs, so that we will find some number of points which are called critical points, right? So we identify critical points at first, and then we go for second derivatives. Then we go for second derivative. We have to find r, fxx, and t, fyy, second derivative with respect to y and again y, s, fxy or fyx. You can find r, t, s, this. Then use in this formula, we call this discriminant d, rt minus s square. For every critical point, we have to check this condition first. If this is positive, if the discriminant is positive, then there is either a maximum or a minimum, either a relative maximum or a relative minimum. Second condition, if this condition is true, then we have to verify part A, r value, what is second derivation with respect to x. r value, which is fxx at the critical point x0 y0. If this is negative, you get maximum. If this is positive, you will get minimum, just like our calculus 1, isn't it? So if d is discriminant is positive, it means that there is either a relative minimum or a maximum. So how do you conclude this minimum or maximum? Then check the sign of r. Is it positive or r is here? Sign of r. If the r is negative, you get maximum at the critical point. If the sign is positive, you get minimum at the, so they are opposite to each other. That's the concept. Fine. Next question is, if discriminant d is negative, that is point C here. If the discriminant d is negative, we call the critical point a saddle point. We call that critical point a saddle point. Is it neither maximum nor minimum at this point? Okay. And d. If d is neither positive nor negative, then there is a chance d is 0. When d is 0, this method fails. We cannot conclude anything by this method. We have to physically analyze the graph. Right. That's what we are going to do in this chapter. To find relative extrema. Okay, not for absolute. Okay, what's the first step? Find d, discriminant. If this is positive, check the sign of r. If it is positive, then you get minimum. If it is negative, you will get maximum, right? If d value is negative, that is, the point is called a saddle point. If d value is equal to 0, then this method fails. Okay. Next. Okay, here we go. What we wanted to discuss here is, if we know that by the previous theorem, if a function of two variables is continuous on a closed and bounded set R, then the extreme value theorem says that there is an absolute maximum or an absolute minimum for the function in this given R, isn't it, region. And one more point, the absolute extrema can occur either on the boundary points. There is an R. The absolute extrema can occur on the boundary points or some interior points. If there is an extrema in the interior point, by another theorem, it should be at the critical points. So what we have to do to get the absolute extrema is given here. Find the critical points that lie in the interior of the region. Find all boundary points at which the absolute extrema can occur, and find the value of the function at all the given points, and then the largest value of all this is called absolute maximum, and the smallest value of all this is called absolute minimum. That's very trivial, right? Let's start exercise 13.8. Here there are two problems. So we solve one here right now, and the other one is your practice problem. Complete the squares and locate all absolute maxima and minima, if any, by inspection. Then check your answers by using calculus. This is for absolute maxima and minima. Okay. Fine, let's try this one. What we got to do here is to find the complete square. Let me start with the problem number 3. F of xy. I rewrite the function in such a way that I'll get x square. I separate this 13 into as, see, the x square minus 6x plus 9 plus y square plus 4y plus 4. See, this 9 and 4 is 13. This 9 and 4, this 13 has been separated to 9 and 10, so that the first 3 terms will be a perfect square and second 3 terms will be another perfect square. Again, write this one. x minus 3 whole square. This is f of xy. Plus here this is y plus 2 whole square. Now the question is, what is the possibility for this function? What we get from this function? Do we get maxima or minima? See, all the terms are square terms, so there is no way to get a negative value. Whatever the given input for x and y, you will get a positive answer. So y increases, f will increase. So you are moving towards the maximum. There is no maximum. For every increasing x and y, the value of f increases, isn't it? So we cannot finalize the maximum. It's keep going. Okay. Now question is, can we find a minimum most value? There is no negative value possible, isn't it? Because every term is a square term. So minimum most value occurs when x is equal to 3 and y is equal to negative 2. Y is equal to negative 2. So its range is all values of x and y. Therefore the domain is xy plane. XY plane. But at this point x is equal to positive 3, y is equal to negative 2. We know that the function gets a minimum value, which is f of 3 comma negative 2, it is 0. By our inspection we found it, isn't it? Now we can find, there is no boundary value to find the absolute maxima. So isn't it, boundary value as far as y and x keep increasing, the f will be increasing. So no maximum. So some interior point 3 comma 2. So we have to find critical points for this function. First derivative fx, derivate with respect to x. Second term 0, you get 2 times x minus 3 into 1. What is fy? First term will be 0, second term is 2 times y plus 2. So take here, let fx equal to 0, what do you get? 2 times x minus 3 is 0, x is equal to 3. In the similar ways, take fy is 0, you will get y is negative 2. So critical point is 3 comma negative 2. Isn't it? So at this critical point, what we find, the minimum, the value of the f is 0. So by the previous method discussed here, we found only one value, which is minimum, and there is no absolute maxima for this function, only absolute minimum. That's it. Next, this contour plot. Okay, the contour plot show plots. There are many contours. Show all significant features of the function. Make a conjecture about the number and the location of all relative extrema and saddle points, and then use calculus to check your conjecture. Okay, if you look at this graph, the function is given here. X square plus 2y square minus x square y. X square y. What's going on here? It is okay. See, this is going downwards. These curves are showing that the minimum most point, maybe that is downwards it's going, isn't it? It's a contour, level curve of a trench or something, this one. So this is going downwards. This minimum most may occur at 0, 0. This is 0 and 0, and no possible maximum can be found from the graph. It's going upward, isn't it? So probably there may be saddle points at which there is no maximum or minimum. Okay, we will estimate it from the this one, fx. Find first derivative, you will get 2x minus 2xy. take it 0, you will find 2x is outside, 1 minus y is 0. X is 0 or y is 1. This is the first conclusion you got. Second derivative, second again, fy derivate with respect to y. This will be, first term is 0, second term will be 4y minus 2xy. 4, no, we are differentiating with respect to y, so this is x square. And take it 0, first derivative make it 0, so you get 4y is equal to x square. So there are two results, this is 1, this is 2. X 0 gives y 0. So 1 point we got is 0 by 0. This is the first critical point. See, this x equal to 0 should be used in equation number 2. Then 4y is 0, obviously y is 0. Next, when y is 1, x square is equal to 4x is equal to plus or minus 2. So we can find the 3 points from this one. X is positive 2, y is 1. X is negative 2, y is 1. So there are 3 critical points. 1 is here, 2 are here. So there are 3 critical points. You can find it here. The first 0, 0 we found a minimum most value. We will check it by using calculus. And we know this is given that 2 at this axis 2, where is the x-axis, what is the y-axis? Probably this will be the x-axis. This will be the y-axis. So a 2 positive 1 at this point is neither maximum nor minimum if you take a round circle in this point. And another point here it is negative 2. So this point, at these 2 points you find no maximum, no minimum. Let's check it by using the calculus. So we have found the first derivatives. We have to find second derivative r, which is f double x, t, which is f double y, s f xy, and then we analyze the discriminant d for all the 3 points. Okay, let's go ahead. So remember the first derivative from which we will find second derivatives. Fx and fy should be noted down. Now I'm writing the second derivatives. What is second derivative? Fxx from the first derivative. When you continue to differentiate, we call it r. This is 2 minus 2y. So this is our r. And t, f double y. Differentiate fy again with respect to y. So you get 4 y will be 1 and then x is 0. So this is t. Next is s, fxy or fyx, anything. You can take fx, differentiate with respect to y, it will be fxy. You can take fy, you can differentiate with respect to x, it is fyx. Anything is good, right? So what is s, second derivative? Is it negative 2x? Check your answer. There are 3 terms. Now we know that discriminant d is rt minus s square. This is going to be calculated for every critical point. We have 3 critical points, 0, 0, critical points, 0, 0, positive 2, 1, and negative 2, 1. These are the 3. So for the first point, critical point 0, 0, x is 0, y is 0. Find r. What is r? r 2 minus 2y, 0 is 2. T is constant, no x and y. S is minus 2 times x, so 0. It is 0. So what is d? D is rt. R is 2, t is 4, minus s square is 0 square, so it is positive. So there is either a maxima or minima. First condition is positive. So next we will check R. If D is positive, there is a maxima or minima, relative maximum. So we check R value. R is positive 2. Therefore we get minimum. We call it relative minimum at the point 0, 0. See, this point will give you minimum. In the similar way, we will analyze in the similar way. You do the remaining work. Try R for the point 2, 1. I will show you R. 2 minus y is 1. So 2 times y is 0. R is 0. And t is 4. There is no x and y. S is negative 2 times x. X is 2 minus 4. So what happens for RD? RT minus S square. RT. R is 0. T is 4. RT is 0. Minus 4 square is 16. Negative 16. So D is negative. When the discriminant is negative, so there is no maximum nor minimum. We call it saddle point. Saddle point. So this point 2, 1, positive 2, 1 is a saddle point. In the similar way, you can check negative 2, 1. You will get a saddle point again. So let's go for the next problem. There are 4 problems. We take only almost the same method is going to be repeated. So I would like to give only one example out of this 4. The same method I have to repeat. Find fx, find fy, equate them to 0 to get the critical points. After getting critical points, x and y values, just pair them to get all the critical points. Then you find r, which is f double x, t, f double y, s, fxy. Then discriminant d is rt minus s square. For every critical point, we have to verify this one. If this is positive, then verify r. If it is negative, you get maximum. If r is positive, you get minimum. If d itself is negative, we call it saddle point. If d is 0, we say no conclusion. And let's see one example from this collection. Because we are repeating the same method, I don't want to solve all the problems. I leave these 3 for you to practice. I solve this problem, and then we go for application type problems. Okay, problem number 19. What is the first step we need to do here? Problem number 19. Fx differentiate partially with respect to x. E raised to minus x square plus y square plus 2x. And then chain rule, so differentiate the power. So it is with respect to x, isn't it? So there is a negative outside. 2x, x square will give you 2x, and the 2x will give you 2, negative 2 times 2x plus 2. This is first derivative with respect to x. We have to take it 0. Okay. See, fx is 0 gives only negative 2x plus 2 is equal to 0. The exponential cannot be 0. We know e raised to minus infinity will be 0. That is, in the power of exponential e, you should have infinity. Then only this e will be 0. That is, no finite value of x and y makes e power minus x square plus y square plus 2x as 0. So this is not possible to be 0. E raised to this term cannot be 0. So if fx to be 0, then only this term becomes 0. Therefore, what is 2x is equal to minus 2, and x is minus 1 is the first value. We got it. And then we find fy. Differentiate f with respect to y. The same exponential e raised to minus x square plus y square plus 2x, and then differentiate the power by y. Chain rule, isn't it? X square will be 0. This minus also, so 2y, and all other terms involving x will be 0, isn't it? Again, if you take let fy is 0, similarly exponential cannot be 0, only negative 2y should be 0, therefore y is 0. So by finding first derivative and taking them to 0, we got the values of x and y. So the only critical point is negative 1 comma 0. So we have to verify the discriminant only for this point, negative 1 comma 0. Okay, we have to find second derivatives. Remember this output of first derivative. We had to use product rule. Product rule. We are going to use product rule for this one. The next page, isn't it? Okay. Okay, what's next? Second derivative. If we call it r, f double x, we know fx. You just differentiate it by using product rule. This e raised to minus x square plus y square plus 2x can be returned, and then differentiate negative 2x plus 2. Negative is outside. When you differentiate 2x plus 2, you get 2. And then keep this negative 2x plus 2 safer. Using product, we are using product to differentiate the exponential, get e raised to minus x square plus y square plus 2x, and then differentiate the power by chain rule. You get again minus 2x plus 2. We don't want to simplify this one. We just want the value. We have only one critical point. What is it? The critical point is negative 1 comma 0. So at this negative 1 comma 0, what is r? R at negative 1 comma 0. X value is negative 1, y value is 0. That is fxx at negative 1 comma 0. Wherever x comes, substitute negative 1. See, here e raised to minus x square is negative 1 square is 1, y square is 0, plus 2 times x is negative 1, so minus 2. And the coefficient is minus 2. This side, 2x plus 2, x value is negative 1. So 2, 1 minus 1 is minus 2 plus 2, 0. So everything will be 0. So r value is obviously negative 2. This is 1 minus 2 minus 1, 1 minus 1, e raised to 1. That is e. R is 2, negative 2 times e. Actually r is negative. Find t. Second derivation of f with respect to y. In the similar way you can try. First write the exponential term as it is x square plus y square plus 2x, and then differentiate the negative 2y. It will be negative 2. Now keep the negative 2y and differentiate the exponential e raised to minus x square plus y square plus 2x. Differentiate the power. With chain rule you get minus 2y, isn't it? Now again for t, substitute the points. Find t at the point negative 1 comma 0, that is f double y negative 1 comma 0. X is negative 1, y is 0. In this derivative, e raised to minus 1 minus is outside, 1 plus y is 0 minus 2 into minus 2 plus second term will be 0 as y is 0. Second term will be 0. So the answer for t is again minus 2 e power 1. This is second result, isn't it? R and t. We have to find second derivation. Yes, s fxy. So remember r and t. Negative 2 e raised to 1, isn't it? Let's try s. S is coming up. fxy. Take fx, differentiate with respect to y, or take fy, differentiate with respect to x. Both are equivalent, isn't it? fxy or fyx will be, what is the term? So differentiate it. You will get take fx and differentiate it with respect to y. keep the minus 2x plus 2 and differentiate the exponential e power minus x square plus y square plus 2x. And when you differentiate the exponent with the power with respect to y, you will get 2y negative. And now chain rule, no, second chain rule is not possible because this term does not have y, so that should be kept. Only exponential has the y, so that's it. Now find s at the negative 1 and 0, that is f x y at negative 1 and 0. X is negative 1, y is 0. When x is negative 1, this term will be 0, and y is 0, obviously this one will be 0, so everything is 0. Check. S is 0, so remember r is negative 2 e power 1, t is negative 2 e power 1, and s is 0. So then what is discriminant d? For the critical point negative 1 comma 0, discriminant d is rt minus s square. R is negative 2e, t is negative 2e minus 0. So this is 4e square, which is positive. E is a positive value. E is 2.7 something. So 4e square is positive. D is positive. Therefore, there is a relative extrema, either minimum or maximum. Check the sign of R. R. What is R? Negative 2e. E is positive, so when you multiply by negative, you get negative. So R is negative. It gives relative maximum at the point negative 1 comma 0. That's the end of this problem. Try other problems yourself. The solutions have been given here. Two application type problems, isn't it? I'll give introduction, and then you have to follow the same steps again. First derivative, second derivative, and then take the first derivative into 0, get the critical points at every point. Okay, let me try to solve one problem for you guys. Find the three positive numbers. So there is no 0, isn't it? No negative values. You are supposed to find three values: x greater than 0, y greater than 0, z greater than 0. Three positive values. Condition they are positive, isn't it? Whose sum is 48. So first equation is getting x plus y plus z is equal to 48, and such that their product is as large as possible. I mean, we are going to find the maximum of the product. So maximize, there is a function to maximize or minimize. This is what we are going to find from every application. Find a function to be maximized or minimized, and generally call it optimize. Okay. The product is maximize the product. We call it maximize the function f, which is the product x into y into z. And we have seen a procedure for finding maxima or minima, relative maxima or relative minima, for a function of two variables, not a function of three variables. So the third variable should be eliminated by using the given auxiliary equation. So let's find z from this equation. This is actually equation number 1. This is equation number 2. The function to be maximized or minimized is the function equation 1. From equation number 2, we can find z is 48 minus x minus y. Use this value in this function equation. So f will be xy times z. Z is 48 minus x minus y. So f is 48xy minus x square y minus xy square. Now for this function we will find critical values, critical points. Find the first derivatives, make them 0, find the critical points, and then second derivatives, try the discriminant, all these things, right? Let's continue with this one. First fx, differentiate with respect to x. You can find 48 y minus 2x y minus y square. Obviously this is fx. Fy with respect to y, differentiate partially with respect to y. 48x minus x square minus 2xy. So we got two partial derivatives with respect to x and y respectively, right? We are going to take them 1 and 2. We are going to find the critical points by equating these two terms into 0. Okay, let's do it this side. If you take fx is 0, what do you get? 48y minus 2xy minus y square is 0. Take y outside. Y is 48 minus 2x fx. You are taking fx. 48 minus 2x minus y is 0. This is y is 0 or 48 minus 2x minus y is 0. This is result A. And remember, y not equal to 0. We are allowed to have positive values of x, y, z. The integers not allowed to be 0. So we ignore this one. So this is the only conclusion from this one we got, isn't it? 48 minus 2x minus y equal to 0. This is our result here. Similarly, from fy, let fy is equal to 0, equation number 2. What you get is 40. This is 48x, isn't it? 48 x is taken outside. X 48 minus x minus 2y is 0, and here x is 0, this is 0, so x is not 0, isn't it? We need positive values of x. So the conclusion from this one is 48 minus x minus 2y is equal to 0. Now solve these two equations. This is equation number B. The equation number A is given here, the equation number B is given here, and this is your task to solve these two two equations by algebraic method and find the values of x and y. Will you try? So I leave this work to you. I write the answer here as x and y values. When you take them equal to 0 and solve these values, you get solve the equation A and B. When you solve A and B, equations A and B, you will find x is equal to 16 and y is equal to 16. Okay, and this is the only critical. Therefore, the critical point is 16 comma 16. Now for this only one critical point, we have to verify D, which is RT minus S square. And remember, what is R? R is second derivation with respect to x. So go back to fx, differentiate it with respect to x again. You will get f double x as negative 2y, and this y is 16, so this is x, this is y, so minus 2 and 16, it will be minus 32. R is negative. Next t, which is f double y, go to fy and differentiate it with respect to y again. You will find it as negative 2x. Now negative 2x is 16, so you will get negative 32. And find s, either take fx, differentiate with respect to y, or take fy, differentiate with respect to x. And both the way you will end up with the same value when you differentiate with respect to x or y. You get 48 minus 2x minus 2y. Now substitute the x and y values. 48 minus 2 times 16 minus 2 times 16. S is 48 minus 32 minus 32 minus 64 is negative 16. So there are three values. R is negative 32, T is negative 32, S is negative 16. Therefore, at the critical point 16 comma 16, we find D, which is here. Negative 32 minus negative 16 square. So the minus 32 into minus 32 will be 1000 and 1024 minus 256. So it's a positive quantity. 768. T is positive, and obviously we have to check the sign of R. R is negative 32. It's lesser. Therefore, we get relative maximum. When R is negative, it is maximum at 16 comma 16 and 116. So the x and y are giving you the x and y, the values of x and y 16 and 16, giving you the maximum value of the product. So obviously find z now. What is z? We have seen x plus y plus z is equal to 48. So x is 16, y is 16, z is equal to 48. Obviously z is also 16. So we have found three positive numbers whose sum is 48. The product is large, is 16, 16, 16. Answer is 16, 16, 16. In the similar way, I will give a clue for the second problem, and then derivatives have to be done by you. I'll give an idea beginning of this problem, and then you will finish it. A rectangular box, a closed rectangular box. You take okay, assume this is the rectangular box, and this is x, and this is y, and this is z axis. The volume of the box is given as 16. So the first function given to is x, y, z is equal to 16. But that is not the function to be maximized or minimized. Read the problem, you will come to know. The top and the bottom are made of, see, this rectangular box is made from two kinds of materials. They are using a different material for top and the bottom, and for the sides there are four sides. 1, 2, 3, 4. The sides, there are four sides. For the four sides they use less quality material costing $5 per square foot. But for the top and bottom they are using some expensive material which is costing $10 per square foot, isn't it? So out of the total surface area, we are going to find surface area. See, the bottom, this surface area is x times y, and with the top is also the same area, so 2 times. So we are finding surface area s 2 times xy. So this is the total area. 2 times xy is the total area of the top and the bottom, because this is again x, this is again y, so xy, again xy in the bottom, 2xy. For the total material for bottom and top, they spend $10 per foot. So for this amount we should for this area we should multiply by 10. Then the total cost you will find for constructing the top and bottom alone. And now $5 per foot for the other sides. So what is the total area of other sides? See, two sides. You can see two sides opposite. These opposite sides we can draw again. If this is the side you are looking for, the area of this side is, this is y direction, this is z direction, isn't it? Zy. So opposite is also zy. So 2 times zy. Similarly, there are other sides. This side. This side we call this distance is x, this distance is zx. Zx and opposite is zx, so 2 times zx. So this is actually the const function, not a surface function. When you don't multiply 10 or 5, it will be surface area. But when you multiply this surface by its cost, it will be cost function. So this is the function which is to be minimized. We are going to minimize. Find the dimensions of the box. So we have to find x, y, z. That minimizes the expenses for the materials. So this is the function to be minimized. Minimize this 20xy plus 10 zy plus 10 zx, isn't it? This is the function to be minimized, and we don't want z, we want a function of 2 variables, so z can be eliminated from equation number 1. Oh, you can take this is equation number 1, this is equation number 2. Equation number 2 gives z is equal to 16 over xy. When you substitute this result 3 in 1, what we get is f, the function to be minimized, isn't it? Yes, function to be minimized is 20 xy, 20 we multiply it, 20 xy plus 10x into y, okay, 10x into 10y is it, isn't it? 10y into 16 over xy plus 10x into 16 over xy. Wherever z comes, we replace it by 16 over xy. So what is the final form of f? 20xy plus 160 over x, 160 over y and 60 over x. Can simplify further, take 20 out, xy plus 8 over y plus 8 over x. This is the function f to be minimized. So we can find the value of x, y and z by finding the fx, fy and take them to 0. Find the critical points x and y, the pairs of x and y, isn't it? And we know that the zeros are allowed because they are 0 or negative sign should be ignored because they are dimensions of the box. For positive values of x and y, find the pairs and then find again r double f double x, t f double y, s f x y, and then try the discriminant d rt minus s square. If this is positive, there is a maximum or minimum. If the r is again positive, you will find maximum, minimum at this point, minimum at the critical point. So the rest of the work has been left to you to try. Thank you very much for patient listening, and then if you have any question, just ask in the comment section or send mails or through WhatsApp. Thank you very much.